Section 3.6, Quantitative Information from Balanced Equations. The coefficients in a chemical equation represent the relative number of molecules in a reaction. The Mol concept allows us to convert this information to the masses of substances in the reaction. For instance, the coefficients in the balanced equation of 2 molecules of hydrogen plus 1 molecule of oxygen gas yields 2 molecules of water, or 2 moles of hydrogen gas plus 1 mole of oxygen gas yields 2 moles of water, indicate that 2 molecules of hydrogen react with 1 molecule of oxygen to form 2 molecules of water. It follows that the relative number of moles are identical to this relative number of molecules. 2H2 plus O2 yields 2H2O is 2 molecules plus 1 molecule equals 2 molecules. 2 times 6.02 times 10 to the 23rd is 2 moles. 1 times 6.02 times 10 to the 23rd is 1 mole. 2 times 6.20 times 10 to the 23rd is 2 moles. So it's 2 molecules plus 1 molecule equals 2 molecules, or 2 moles plus 1 mole equals 2 moles. We can generalize this observation to all balanced chemical equations. The coefficients in a balanced chemical equation indicate both the relative numbers of molecules, or formula units in the reaction, and the relative number of moles. Figure 315 shows how this result corresponds to the law of conservation of mass. The quantities 2 moles of H2, 1 mole of O2, 2 moles of H2O, given by coefficients in equation 312, are called stoichiometrically equivalent quantities. The relationship between these quantities can be represented as 2 moles of H2 is stoichiometrically equivalent to 1 mole of O2, which is stoichiometrically equivalent to 2 moles of water, where the symbol means is stoichiometrically equivalent to. Stoichiometrically relations such as these can be used to convert between quantities of reactants and products. The mole level interpretation: 2 moles of hydrogen is equal to 4 grams of hydrogen going through the periodic table. 1 mole of oxygen is 32 grams of oxygen, and 2 moles of water is 36 grams of water. There is a conservation of mass here because 4 grams plus 32 grams yields 36 grams. For example, the number of moles of water produced from 1.57 moles of O2 is moles of water equals 1.57 moles of O2. There's 2 moles of water in 1 mole of oxygen yields 3.14 moles of water. As an additional example, consider the combustion of butane in the fuel disposable general purpose lighters. 2 butane moles plus 13 moles of oxygen yields 8 moles of carbon dioxide gas and 10 moles of water. Let's calculate the carbon dioxide produced when 1 gram of butane is burned. The coefficient in equation 313 tells us the amount of butane consumed is related to the amount of carbon dioxide produced. 2 moles of butane is stoichiometrically equivalent to 8 moles of carbon dioxide. 2 moles from the balanced equation in front of butane, 8 in front of carbon dioxide. To use this stoichiometric relationship, we must convert grams of butane to moles using molar mass of butane at 58 grams per mole. This only works when you put it through moles. Moles are related to moles. It's 2 moles is equivalent to 8 moles. It's not 2 grams equivalent to 8 grams. So moles of butane is 1 gram of butane is what we're given at 58 grams of butane per mole. Grams cancel, leaving you 1.72 times 10 to the negative 2 moles of butane. We then use the stoichiometric factor from the balanced equation to calculate moles. Moles of carbon dioxide is 1.72 times 10 to the negative 2 moles of butane, and there are 2 moles of butane for every 8 moles of carbon dioxide. The moles cancel. When you multiply that, you will find it'll be 6.88 times 10 to the negative 2 moles of carbon dioxide. Finally, we use the molar mass of carbon dioxide, 44 grams per mole, to calculate the carbon dioxide mass in grams. The grams of carbon dioxide is 6.88 times 10 to the negative 2 moles of carbon dioxide, and there's 1 mole for every 44 grams of carbon dioxide. Moles cancel, leaving you 3.03 grams of carbon dioxide. This conversion sequence involves 3 steps, as illustrated in figure 316. These 3 conversions can be combined in a single equation. Grams of carbon dioxide. You start with 1 gram of butane. There are 58 grams of butane per mole, so you go to moles first. Then you go through the balanced equation and you find that there's 2 moles of butane in the balanced equation for every 8 moles of carbon dioxide produced. Moles cancel. Now you go from moles, you go back through the periodic table, and there are 44 grams of carbon dioxide in every mole. Moles cancel with moles. When you multiply it all, you'll get 3.303 grams of carbon dioxide. Figure 316, procedure for calculating the amount of reactants consumed or products formed in a reaction. The number of grams of a reactant consumed or product formed can be calculated in 3 steps, starting with the number of grams of any reactant or product. Notice how molar masses and the coefficients in the balance equation are used. Starting with grams of the substance, use the molar mass from the periodic table to find moles of substance A. Then you do the equivalence based on the balanced equation to find the moles of substance B, and then you go back through the periodic table using the molar mass to find grams of substance B. To calculate the amount of oxygen consumed in the reaction equation 313, we again rely on the coefficients of the balanced equation for our stoichiometric factor. 2 moles of butane is stoichiometrically equivalent to 13 moles of oxygen. So grams of oxygen from 1 gram of butane, butane going to moles is 58 per mole, grams cancel. Then it's 2 moles of butane for every 13 moles of oxygen, moles cancel. Then you go back through the molar mass and find that it's 32 grams per mole, moles cancel, times 32 is 3.59 grams of oxygen produced.